Okay, so finally we are going to look at a specific example of finding the area under a arbitrary function, a function that's continuous on the closed interval from a to b. And so we finished the last video with this, right, that these different approximations that we create by these the partition, breaking up the interval from a to b into n subintervals, and creating rectangles whose heights are determined by either the right endpoint, the left endpoint, or the midpoint. Each one of these, if there exists a value L such that the limit as n goes to infinity, in other words, as the number of subintervals increases without bound, and of course by the way we've been looking at it, if the delta x, the width of the subinterval, is going to go to closer and closer to zero, right? Getting closer and closer to zero as n goes to infinity. It's getting the rectangle's width is getting smaller. But if this limit exists and is equal to L, and the function is positive above the x-axis, the outputs of the function are positive, then we actually can define the area under the graph to be the value of L. That is the area of the graph. And so we're going to do that. I'm going to mainly look at right-hand sums when I do this because they're just generally easier than the left-hand sums a little bit, and certainly the midpoint sums, as we looked a little more complicated expressions for midpoint sums that we looked at the end of the last video. So before we go there, we looked at summation notation and the linearity properties in the last video. I want to extend on that and talk about the so-called power sum formulas. Now, you do not have to memorize these formulas. These would be given to you in any quiz or test. But they're very interesting, and I'm not going to prove these. These can be proved. If you want to see that, you can probably Google and see an example. I'll be glad to do that privately with you at some time, or in a Zoom meeting one-on-one or something like that. But the first one says, if I look at this notation, remember the summation notation, I equals 1 to n of I. What's that going to be? So I is 1, and then I is 2, and then I is 3, all the way up to n, and then we add them all up. So in other words, you're just adding the first n numbers. You know, so if I'm going from I equal 1 to 10, that's the sum of the numbers 1 through 10. And it turns out that sum can be written as this expression here, which is whatever the value of n is. So if n is 10, if I'm adding the first 10 numbers up, it's going to be n, which is 10, n plus 1, what's that? 11, right? 10 plus 1 is 11, divided by 2. So 10 times 11 divided by 2, 10 divided by 2 is 5, 5 times 11, 55. So the sum of the first 10 numbers is 55. Now that's pretty powerful. If you can remember this little formula, it's not that hard to remember. You can impress some people, right? If n is 100, what do you get? Well, you can do it pretty quick, right? 100 divided by 2 is 50, times 101, that's 5,050. The sum of the first 100 numbers is 5,050. Done. Okay, pretty impressive. Now, if I distribute the n here, I get n squared plus n, and then if I break up the fraction into two fractions, n squared over 2 plus n over 2, right, I can write it this way. I generally like this form of it. You can use this form too, but this is the form I will actually use in the examples. Now similarly, we have the sum of the first n perfect squares. So this would be the sum of 1 squared plus 2 squared plus 3 squared up to n squared. So the formula there, a little more complicated, maybe not easy to memorize like the one above. And then here's the expanded version if I distribute and expand out the top and break it up into 3 fractions. And then there's one for the sum of the first n cubes. Okay, again, a little more complicated in the expanded version. So we will use all 3 of these in different situations later in the course. But I am going to make use of one of these at least in the next example. Okay, so let's take a look at this example. let's find the area above the x-axis and under the graph of the function f of x equals x squared plus 2 over the interval from 0 to 4. Okay, so I'm going to shade in that area that we're looking for. So what's the area of the region that I've shaded in here? Okay, and you can use, the idea that each one of these blocks is what? 5 tall, right? 1 wide, so they're 5 square units. You can kind of estimate how many blocks are in there and get a rough idea of the area. You could do that, and that's a good intuitive sense. But we're going to find the right-hand sum in doing this and use that as the approximation. So I'm going to find r sub n, and once I do that, then I'll take the limit as n goes to infinity. So if you remember the formula for r sub n, in the last video we derived it right here, right? This is the sum of the areas of those n rectangles. Their widths are all delta x, and the heights are determined by the right-hand endpoints. And if you remember, the delta x is the width of each subinterval. Sorry, I'm trying to get back to that page where we're setting up the general problem. And there it is, right? The delta x is determined by the length of the interval divided by n. Okay, and then the right-hand endpoints, we can see how they're written here, and we'll talk about how to do those in general. In fact, I think I haven't talked about that, so I'll talk about that here. Let's talk about that. So we're going to find the right-hand approximation with n, right? N arbitrary subintervals. And in fact, if you remember from the first video, I had the formula for Rn and Ln for that one example. Go back to that real quick. For different values of n. Right, remember this right here. For the example, we were using the function 1 over x from 1 to 5, and we were doing the right-hand and left-hand sums, right? And so how did I get these numbers? I'm going to show you how you could do that by first finding an expression in terms of n for r sub n. So first of all, our interval, right, goes from, we say, a to b. So a is 0 and b is 4. And therefore our intervals, or subintervals rather, when we partition this up into n subintervals, we'll have what with b minus a over n. And so that's 4 minus 0 over n, which is, of course, 4 over n. So there's our delta x. Now the right-hand endpoints, let's talk about those. I want to look at the arbitrary one. So what is the ith right-hand endpoint? So when you start off, the x sub 0 is going to be 0 here, and then the next endpoint for the first subinterval will be x sub 1, right? And then x sub 2, x sub 3, x sub 4, all the way until we get to x sub n, right? So the first interval will be from x sub 0 to x sub 1, and therefore the right-hand endpoint is x sub 1 for the first interval. The right-hand interval for the second is x sub 2. Well, here's the way that you can write out the ith one. It's going to be whatever a is plus I times that delta x, which is the width of the subinterval. So when I say I is 1, I get a, which is 0, plus delta x. So I just move over delta x, right? And I get to the right-hand endpoint, that's x sub 1. And that's going to give me the information I need to find the height of the rectangle, since I'm using right-hand endpoints. For when I is 2, I get a plus what? 2 times delta x. So that will move 2 over, right? And I'll be at x sub 2, which is the right-hand endpoint for the second subinterval. X sub 3 is the right-hand endpoint for the third subinterval, and so on. All the way until I is n, which we will get x sub n, which of course in this case is equal to 4. So what is the x sub i's then? A is 0, I times delta x is 4 over n, and so it's 0 plus 4I over n if I multiply. Okay, and there it is. Notice it does work good. If I plug in n for I, what do I get? 4n over n, that's 4. That gives me the right-hand endpoint for the last subinterval, as it should be 4. Okay. All right. So what is the right-hand sum? Well, I showed you the formula a little while ago that we derived last time, and here it is. It's the sum, I equal 1 to n, of the areas of those n rectangles. The heights are f of x sub I, right? The height of the rectangle determined by the right-hand endpoint, times their width, which each one has the same width, delta x. So let's plug in these values that we have. F of x sub I. So what is f of x? F of x is this function right up here, x squared plus 2. So this is f of x sub I is 4I over n times delta x. And what's delta x? 4 over n. Okay. So now what is f of 4I over n? What is that? This little bit right here. Well, I'm going to plug it into the function x squared. So whatever I have as an input, I'm going to square it and add 2. So the input is 4I over n. I'm going to square that and add 2. Just evaluate that function at that expression. If I square 4I over n, I get 16I over n squared plus 2. Okay. And so what I'm going to do now is I've got, so this is really in parentheses, if you will, right? Right here. And this is multiplied by 4 over n. So I want to distribute 4 over n over, use the distributive property, and expand this out. So I'll have the summation I equal 1 to n. 4 times 16 is 64. I times I is I squared. N times n squared is n cubed. And then 4 times 2 is 8 over n. So just 2 times 4 over n. So see what I've done? I multiplied 4 over n times 16I over n squared. And then 4 over n times 2. And so here's my summation. Okay? So that's what you want to do. You want to evaluate the function, and then you want to, multiply by delta x. Okay, that's one way you could do it. We could do some other things, but this I'd like to do it this way. Now I have what? I want to use my linearity rules for sums. Remember this. So the summation I equal 1 to n of something plus something, like a sub I plus b sub I can split this up into the sum of two things. Okay, and then I can use the other linear principle, that is, if I have a constant multiple, I can pull that out. Now, what do I mean by constant? Anything that doesn't involve I, right? Anything that doesn't involve I. So I can rewrite this as 64 over n cubed is a constant multiple, leaving I squared. And here I can pull out the 8 over n. What does that leave me? Just 1. This is important. 1, not 0, right? It leaves me 1. Okay. And now we're ready to use two things. First of all, here I'm going to use the power sums that I was just talking about. And I'm going to use the one where I'm adding the squares, the first n squares. And so if I add the first n squares, what do I get? So what am I going to do with that? Let's go back to the previous page and we'll see again that formula that we have. This will be given to you, right? Sum of I squared, I equal 1 to n, is this thing. And you can do that, but I'm going to write this the expanded form. I like that a little bit better. So I'm going to use the power sum formula here. And so I get n cubed over 3 plus n squared over 2 plus n over 6. So that's basically what has happened to this part right here has become all that. Plus 8 over n times what? Well, what is the sum I equal 1 to n of 1? Well, that's 1 plus itself n times. That's just n times 1, or n. Okay, so I'm multiplying 8 over n. This is just n. Okay, and lo and behold, I now have what? I've gotten rid of all my summations. What do I have? Just an expression involving what variable now? N. Right? And there it is. I'm going to simplify this a little bit now, just to help. And I'm going to simplify by distributing this thing through here. Multiply by these three. And so I get, notice here, 64 over n cubed over 3. The n cubes cancel, and I just have 64 thirds. Here, 64 divided by 2 is 32, and I have what? N squared divided by n cubed leaves 1n on the bottom. 32 divided by n. And then here, the n's, I leave n squared on the bottom, and 64 sixths. That simplifies down what? 2 divides evenly into those. 32 goes, 2 goes in 64 32 times, and 3 times. And we have an n squared left over. What happens here? 8 over n times n is just 8. Okay. And so finally I can clean this up just a little bit more, just because I want to. 64 thirds plus 8 is 64 thirds plus 24 thirds. 64 and 24 is 88 thirds. That is my right-hand and approximation now. Okay, and I like this form, just compact. And now, you remember how I showed you that table of values that I had for the other problem? You can now do a table of values for the right-hand approximation, right? If you were to draw, say, 4 rectangles, or 8 rectangles, or 20 rectangles, or whatever, for this function over this interval 0 to 4, what would the sum of those areas be, where, again, the heights are using the right-hand endpoints? The answer is, you just plug in here. If you have 4 subintervals, n is 4, replace n with 4, evaluate. N is 10, plug in 10. If n is 100, plug it in. So here's a formula. There it is. You can approximate that. But what we are saying then is that this this approximation, this right-hand sum approximation, this R sub n, as n gets bigger and bigger, this is going to approach the actual area under the curve, if that limit exists. Okay? Because again, our function here is continuous, and it is always positive. In other words, it's above the x-axis. So when we take the limit, we're going to get this actual area. And so here it is. The area under the curve is equal to the limit as n goes to infinity of this, which is the limit as n goes to infinity of 88 thirds plus 32 over n plus 32 over 3n squared. Now you have to remember how to find limits at infinity from Calculus 1. Do you remember how to do that? What's going to happen to the 88 thirds as n goes to infinity? Well, nothing, right? It's just 88 thirds, right? It's going to stay the same. What's going to happen to 32 divided by n? Well, as n goes to infinity, n gets bigger and bigger. 32 over n is getting closer and closer to what? We say the limit is what? This is going to go to what? 0. Right? 32 over 3n squared, again, n squared is going to get bigger and bigger, so again, this is going to what? 0. And so what's our limit? 88 thirds. 88 thirds. That is the area under that curve. And now, you can find the area under the curve of any continuous function that is above the x-axis. Well, I say any. You're really not any. There's many that we can't do right now, but we will learn how to do. Right now, we can only do ones that are polynomials, essentially of degree 3 or less. We can't do like trig functions, exponential log yet. We'll be able to do those later. But this is a start. Okay, so we're going to do this type of problem a lot more in the coming lectures, so you'll get some more exposure to this. But this is our mission is accomplished, finding the area under an arbitrary curve.